Hi, everybody. We're back for another installation of my stats course, your stats course. So here's right where we left off, and we were going to get a z-score for Bob. Remember, Bob sort of insisted that his reaction time of 3:33 here was not representative of his real reaction time. So we decided to let him do 3 trials. We calculate Bob's mean, and here it is. Okay, this is just what I provided you. And the question then was, because this was based on three trials, right? We're going to see if Bob is in the weird category again. So we can just calculate that by getting a z-score for Bob based on his sample and based on this sampling distribution of the mean. So now in this case, we're going to do, let me get a piece of paper. Hold on. So we're going to just use our central limit theorem here once again and use the z-score that looks like this. Okay, so Bob's mean of 280, we're going to compare that to 258 for samples of 3 from normal people, okay? And then the new standard deviation, it's not this one. This is for individuals. This is for samples of 3, okay? 27 is the standard deviation for individuals. For samples of 3, we're going to do 27 divided by the square root of 3. So that becomes 15.61. Now this is Bob's z-score. Let's calculate this. 280 minus 258 equals 22 points above the mean, but the standard deviation here is 15.61. And so Bob's got a z-score of 1.41. So that doesn't fall in the extreme 5%. You know, he's going to be here somewhere. And so I'm going to be like, oh, well, we made an error when we just gave Bob that one test, the one reaction time test. We made a bit of an error in assessing that he was weird. Hopefully this better represents his canvas bag, okay? And so I would say he falls within a normal range. Okay, it's still 1.4 standard deviations away from the mean, but not enough for us to say, hey, something is going on here. Okay. A couple of somebody emailed me, and so I wanted to clarify. Most of what I'm talking about here is Chapter 7. That's central limit theorem. Of course, you should have already read Chapter 6. That has to do with probabilities and using the z-score table and all of that stuff. That should be down pat at this point. But I do want to note, and I'm glad somebody had emailed me, the section in Chapter 6 that has to do with something called the binomial distribution. The binomial distribution. We're not going to cover that. It may be important to you at some point. I don't know where you're going to be working or where you're going to graduate school or whatever. But hopefully you could figure it out on your own if you need to. I guess what I'm saying is I'm not going to be asking anything about the binomial distribution on an exam. And the only reason I'm cutting that out is because we have other things to do that we're not going to get through. so I've chosen not to cover that. So the section on binomial distribution, don't worry about it. There will be some homework problems at the end of chapter 6 that have to do with the binomial. Don't worry about that, okay? Also, I'm going to assume that you guys are okay with this now in terms of the math. If you have an individual score, you use the z-score that we've been using for individuals. Hold on. Which is z. You take this person's score, you compare it to the mean. I'm going to get rid of this. I'm going to get rid of everything, looks like. Sorry about that, folks. Okay. Take the person's score, you compare it to the mean, put it in terms of standard deviation. Okay. That's old stuff, should be all review. If we have a sample, then we're going to take the sample mean, compare it to the mean for all the sample means, and put it in terms of standard deviation for all the sample means. We're basically just sort of emming everything, right? We're sort of emming everything. By the way, the book erroneously, and I hope this doesn't confuse people, if you're looking at a sample mean, mean of all the sample means, standard deviation of all the sample means, right? It makes sense. If we're looking at individuals, individual score, mean of individuals, standard deviation of individuals. Everybody good? The book erroneously puts this value here. I say erroneously because when you're comparing a sample, it's sample mean to the mean of all the sample means, okay? It doesn't make any sense to go back to the originals. But the thing is, these two values are equal. And so the authors of the book they're a little bit sloppy. They're sloppier than me. This is the formula for samples. This is the formula for individual scores, okay? All right. Also, I'm assuming you can do the math, but I would encourage you to do the problems at the end of chapter 7, because there will be all sorts of problems like the ones I just talked about with IQ and with Bob's reaction time. There's all sorts of problems like that. So if you want to feel better, getting that done, please do so. Also, if you have any questions about the specific homework problems, feel free to email me, and we can start the next video with one of those questions. Okay, so that's up to you to get done. Again, I don't assign homework. It just doesn't. It's too much like high school. If you want to do well, do some of those practice problems. That'll help you with the computational. I'm sort of here to help you most with the conceptual work, all right? So, done with chapter 7, okay? Let me know if you have questions about that, and I can answer them on the next video for everyone. And I'll also answer questions individually, but if somebody has a question, it's likely that a number of you do, like I said in the first week of class. That doesn't bother me at all. Okay, so now, finally, I think that we're ready for some really cool stuff. We're going to put everything together. We're putting everything together now, and we're going to start doing some research. Okay, I'm going to try to use all sorts of different examples that some of you can relate to in different majors. We're going to do psych examples. We're going to do PT examples. We're going to do neuroscience examples. All sorts of stuff, and hopefully you'll see the pattern of how this stuff works. The next this video and the next video are once again going to be a lot of conceptual stuff because Chapter 8 is a lot of conceptual. We're going to use some of the math, some of the computational to answer some of our questions. Okay, let me set this up for you. And I'm hoping that, I'm hoping that this will be accessible to you or something that might be considered cool, I guess. I don't know. So I have my PhD in psychobiology, and my work, I went to Binghamton to get my PhD, and a lot of my work was rat work, neuroscience stuff. When I got my first job, my first faculty position, excuse me, in Pennsylvania, I was hired as a neuroscientist, and I worked with rats. I soon became prohibitively allergic to them, and this is a little life lesson that's worth thinking about, I think. I'd worked for 6 years to become a psychobiologist and work with rats, and I couldn't work with them anymore. I mean, it was bad for my health. I was having terrible lung problems, and so I had to switch my whole area of interest, and I couldn't do what I prepared to do for many years. So you have to be careful. You can't pigeonhole yourself into one thing. You have to be a little bit flexible because sometimes you don't have control over the situation. Anyway, I started to do research in taste perception, okay? And so I was interested in what sorts of things, what sorts of variables influenced people's perception of different solutions. And so I would give people, one of the things I would do is I'd give people a 4% sucrose solution. Now 4% sucrose in water is pretty mild. I mean, it would be, you probably wouldn't like it. It's mildly sweet, okay? But I'm going to give people the solution, and then I'm going to ask them to tell me, okay, how sweet does this taste to you, okay? And the instrument that I used to measure how sweet it tasted to someone was something called a visual analog scale. And I mentioned this in class in the first week. You know, how do we go about making measurements of different variables? If you recall, I talked about hypothetical constructs being converted into something measurable, into a operational definition, okay? And so one of the things that I did, I gave people the solution. I said, how sweet do you think this is? So I gave them a visual analog scale. It looks something like this. Let me pull this screen down. There we go. Less backlighting. And so after this is called a visual analog scale. It's not digital, it's analog. I'll show you why in a minute. I'm not asking people to pick a number or circle a number. Just place an X along this line. This line says not sweet, and then over here, very sweet. And so the person would taste the solution, and then they put an X here, for example, okay? And somebody else might drink the solution, and they would put an X here, right? And so this person with the dotted X thinks that it doesn't taste as sweet as the person with this bold X here thinks it's very sweet. Well, I still need to quantify this variable. Until I quantify it, I can't see if there's a difference, or I can't tell what kinds of influences different variables have. So I'm just going to take a ruler here, and I'm going to measure in millimeters how far along this is. So this is about 70 millimeters. And then the bold one is about, let's say, 128 millimeters. So that gives me my measurement. Do those numbers have any intrinsic meaning? Not really. But if this entire line is, what, about 200 millimeters, it's just telling me that this person is rating the solution as more sweet than this person. Okay? So those are the numbers that I'm talking about. Higher the number, the sweeter they perceive the solution to be. Okay? So, I mean, that's not really statistical, is it, in a way? So I had a student in my lab. His name was Stanley Hewlett. I think he went on to get a physician's assistant degree from Hershey Med School. I'm not sure. I live down near Hershey Med. But he came to me one day and he said, Dr. Specht, I wonder if we put red food coloring in the solution, whether or not that would cause people to perceive the solution to be sweeter. And I said, that's a good idea. Let's do the research, okay? Basically, when you're doing research, you're asking questions in an empirical way. That is, I'm going to collect data. I mean, Stan and I could have argued about this in my office, and he would say, well, I think it's going to cause them to rate it sweeter. And I would say, well, I don't think it's going to cause them to rate it sweeter. And somebody else might say, I think it's going to be rated as less sweet, and so on and so forth. I mean, that's no way to run a science, right? What we want to do is set up an experiment, ask the question by collecting data. So we're going to have some people taste this 4% sucrose solution with red food coloring in it. And we're going to see if there's a difference, right? Delta. If there was a difference between clear and red 4% sucrose solution. Okay? That's the basic question. So that's what we're going to do. And let me do it this way. Let us suppose that, well, let me go back. Because let's do a hypothesis first. Chapter 8 is all about hypothesis testing. And so we're going to do some steps here. So step 1 in our hypothesis testing procedure is to develop a hypothesis, okay? What you think might happen in this experiment, or the question that you're asking, okay? And so here's what I'm going to do. I'm going to do this. I'm going to say, and we're going to make 2 hypotheses. I'll tell you why in a minute, okay? But let's just talk about this one first. Okay? This is, well, we'll get to the name of it in a minute. Okay? The question that I'm asking here really is, if I look at the population mean for sweetness ratings for all people that are going to be tasting clear sucrose solution, then I think that for people that have the red food coloring, their mean is going to be different than the mean for the clear group. Okay? This is my hypothesis. By the way, this is called a non-directional hypothesis. Okay? We might have gone into this experiment. I mean, I think what Stan was thinking about was that if we add red food coloring, we're going to see people rate the sucrose solution as sweeter. Okay? In that case, we would put a greater than sign here. We would say the red food coloring mean, that is the average for how people rate the red food coloring, is going to be different, is going to be greater than what we see for the clear. I have not put that in here. What I've done is I said that I think putting the red food coloring in is going to make some kind of a difference. Okay? It may make the people rate the solution as sweeter. It may make the people rate the sucrose solution as less sweet, but I think there's going to be a difference somehow. Okay? This is called a bidirectional hypothesis test. Okay? These symbols say that I think the red is going to be different than the clear. I'm not making a bet whether it's going to be higher than the clear or lower than the clear. I'm just saying it's going to be different. Okay? So this is called a bidirectional because it's going to allow me to see changes in the sweeter and changes in the less sweet. Okay, I'm going to be able to see either of those. It's called bidirectional. The other way that I describe, if we think the red's going to be sweeter, we would put, let me do it this way. I mean, this is what a directional hypothesis would be, that the red is going to be greater than the clear. The only problem, if I test this hypothesis and I find that the red food coloring decreases, then it's going to give me problems here. So I'm not going to do that. This kind of a hypothesis will allow me to make decisions about whether the red increases the sweetness ratings or it decreases. Okay? So red increasing the ratings is a subset of this. So this is called bidirectional. I can see either direction. Here's the confusing part. Listen carefully. Bidirectional or non-directional. That is, I'm not making a bet on what direction. That sounds a little bit weird, right? Some people call it a bidirectional hypothesis test. Some people will call it a non-directional. Okay? But that's how we're going to do it. Everybody clear? I mean, except for that weird jargon. I just think that red food coloring is going to make a difference, that they're not going to be equal to the clear. Everybody cool? Now, I have this other hypothesis here, H sub 0. And this is this is sort of a weird hypothesis, and it has to do with the logic of decision making and the fact that we can't really prove anything. Okay? In fact, when I teach research methods, and a lot of psych professors will say this, I don't want people using the word prove or proof or proven, because technically you can't prove anything, right? I can't prove to you that a meteor is not going to hit this room. Well, if it hits this room, it's not going to hurt you, but it'll hurt me. I can't prove that to you. I'm pretty confident that it's not going to happen. If I thought there was a chance, I'd get the hell out of here quickly, okay? But I can't prove that it's not going to happen. That's this proof thing. However, here's the weird thing. We can often disprove something, but we can never prove something. We can often disprove something, but we can't prove something, okay, for certain. Let me use a crazy example, okay? Let's suppose that we had a hypothesis that all cows in Oneida County had 4 legs. Okay, well, this is a hypothesis that we could set out, perhaps, to prove, be very careful, okay? In order to prove that, we would need every cow. We need to see every cow. Hello, you have a cow? Can I check them out? Blah, blah, blah. 4 legs, 4 legs, 4 legs, 4 legs. In order to prove that hypothesis, we need to see every single cow in Oneida County. Maybe that's doable, but if we really crank up our research and we say all cows have 4 legs, then I actually can never prove that, right? I mean, I'd have to go to every continent in the world and look at every cow and make sure every cow has 4 legs. I mean, it would be virtually impossible to prove that. Everybody with me? In order to prove something, we need to see every single incident of the thing that we're trying to prove. Yeah. How many cows would we have to see to disprove our hypothesis? Our hypothesis is that every cow has 4 legs. How many cows would we need to see to disprove that hypothesis? Yes, 1 cow. 1 3-legged cow. Poor Bessie. She got 3 legs, okay? It's an utter disgrace. Oh, did you see what I did there? I'm just trying to milk it. Duh. Okay. Don't you miss me in class? Duh. No. So, let's get back to our research here, okay? I'm not going to go about trying to prove this because the logic of decision making is that we can't prove anything. But here's the deal. We can disprove something. And so in the sciences, what we've done is we have made a hypothesis that's called the null hypothesis. H sub 0 is called the null hypothesis. And what I'm going to do here is I'm going to say this. I'm going to negate my research hypothesis by saying that I think that when we put the red food coloring in the sucrose solution, it's not going to be different than the clear. The null hypothesis, that nothing is going to happen, okay? The red food coloring is going to be the same as the clear. Notice that these 2 hypotheses are complementary. That's complementary with an E. This negates this, okay? So what? BFD, right? I mean, I don't get it. Well, listen, if I can disprove this hypothesis, then what? I'm just left with this one. Of course, that's predicated on the fact that these hypotheses must be mutually exclusive. That is, you can't have data that fits in this and this. Okay? That's absolute necessity. So we have to have these 2 hypotheses be mutually exclusive, and taken together, they have to account for all possible outcomes of an experiment. Okay? So they can't overlap at all. And if we take them together, they should be able to account for any kind of outcome in our experiment. I can't prove this, but this is the one I want to speak to. If I use the null, if I disprove this, then I'm sort of left with this. And this is called the experimental hypothesis, but it's also called the alternative hypothesis. What's it the alternative to? It's the alternative to the null hypothesis. The null hypothesis says there's not going to be an effect of the red food coloring. The experimental hypothesis says there is going to be a difference. This is alternative to the null. Okay? So that is step 1 of our research. Okay? That is the first step. Now, for the sake of chapter 8, we're going to test one group compared to some kind of norm or some kind of a reference. So I'm going to do this. I'm going to say, listen, suppose that we know this value, okay, then I know how people rate the clear solution, okay? And in chapter 8, they're going to be starting off a lot of the problems at the end of the chapter. They're going to be starting off by saying, suppose that blah, 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 blah. And then they'll impose some kind of a treatment and see if there's a difference. So here's what I'm going to say. Suppose that we know that people on average rate the clear solution as 80. And in this case, because we're using our visual analog scale, in this case, then we're going to say 80 millimeters. Just it's that position on the visual analog scale, okay? So another way that we could do this is we could say the null hypothesis is saying that the red food coloring is going to be equal to 80. Our experimental hypothesis is that if we put red food coloring in the solution, it's going to change the rating so that it's not 80 anymore, okay? It's going to change that rating. So we could draw it like this, or write it like this, or we could write it like this if you're given this information, okay? The null hypothesis would say the red food coloring group is the same as 80. They have the same mean. The population of people drinking the solution with red food coloring is going to be the same as the population of clear, okay? Now, I'm talking about a theoretical or hypothetical population. It could be that nobody's ever tasted 4% 4% sucrose solution with red food coloring. This is a hypothetical population. This is a canvas bag that I don't know anything about. For the problems in chapter 8, we're going to start off with a given. We're going to say, I do know what the bag looks like for the clear. I just don't know what the bag looks like for the red. Okay? Pretty cool. You can, listen to this again. Here's where we're going to start. I started my research with Stan, and he said, gee, I wonder if red food coloring is going to create a difference in how people rate that. Here it is in symbols, okay? I added the null hypothesis partly because of this decision-making logic that we cannot ever prove this. We can disprove things, so I'm going to try to disprove the null, and then that would leave this as my alternative. It's going to be my conclusion, okay? All right, so that is step 1. Step 2. Step 2 has to do with our hypothesis, our alternative hypothesis. We say, well, and the null, really. What does it mean when we say the people rating the red are rating it differently? What does it mean when we say they're rating it the same? That is, we need to define what we mean by equal and not equal. To go back to our hypotheses, right? Here they are. And so I need to define what I mean by the red is not equal to the clear. I need to define what I mean by the red is equal to the clear. Okay? What do we mean by equal and not equal? Let's take a look. We're going to do that. Oh, this is so exciting. Because it's all coming together, folks. I mean, I don't know if you don't think this is a cool experiment, then you can, think of one that's cool to you. I mean, we might ask people how much they like a movie. And we can show the movie to them without a soundtrack. And then we can show them the movie with a soundtrack. and we could see if there's a difference, right? That might be cool. Or what if you're in business and you say, gee, we usually sell this many products per month, and I want to see if we get a celebrity spokesperson, will that change the amount that we sell? Okay, I mean, just use your own example if you don't like this example. I'm hoping this example is fairly, makes sense. I mean, accessible. Okay, so here's what we're going to do. We're going to put our z-score stuff together. We're going to put our central limit theorem, all that stuff. And here's what we're going to do. Let's suppose that this is the clear solution distribution. Because when I ask people to rate the clear solution, they're not all rating it at 80. That's the average, right? I mean, we've talked about this lots and lots. So I can tell you, we can assume that the average for the clear is 80. That's a given. That's what I've given you. But we also should be aware that there's some variability in the way that people rate the sweetness of this solution. Okay, and in fact, there's lots of variability when it comes to taste perception. There's tons of variability. So let me do this. Let's say that the variability is 12 millimeters. On average, people rate the clear solution as 80, and it has a standard deviation of 12. Okay? Now we have to say, okay, suppose that somebody tastes the red, and that's where they rate it, right? It's above the mean. Does that mean it's different than 80? I mean, suppose they're at 90, let's say. Suppose they rate it at 90. Is that different than 80? Well, I mean, mathematically it's different, right? 80 is not 90. But you guys are much more sophisticated than that now. You know that you don't have to be exactly 80 for you to say, hey, that's expected, that is probable, that's typical, all of that stuff. Remember that from class? We were in class when we were talking about that. Or if somebody rated it at 78, is that different than 80? I mean, mathematically it is, but we're talking about statistics. We're talking about that's probably not different than 80. 90 is probably not different than 80, especially given this standard deviation of 12. This also relates to our flipping a coin, right? When you flip a fair coin, you expect to get 50 heads and 50 tails. But if you got 48 heads and 52 tails, you're not going to be having a fit that coin is unfair. It's not far enough away for you to get worried about it. When you're flipping that coin, you expect 50-50. If you get 55-45, I think that's probably fair. Once you get to like 75-25, then I really start having some concerns that that's not a fair coin. Remember this? It's the same thing here. When we looked at Bob's reaction time, we're like, I don't expect it to be 258 exactly, but it should be around 258. And as it goes further and further away from 258, I would say, hey, there's something wrong with Bob, right? Same thing here. So this is what I expect. This is what I expect from people tasting the clear solution. That's where I expect them to rate it. If my red falls in here, then I'm going to say they're not acting differently from the people who tasted clear solution. Okay? But at some point, we're going to say, hey, this is not what I expect from my clear folks. This is not what I expect from my clear folks. If my red is out here, I'm going to say, boy, they do not look like clear folks. They're too far out, man. Okay? And as statisticians, we've decided, and this is really quite globally and across disciplines for the most part, we've decided that as long as things are in the middle 95%, then we're going to say there's no difference. As long as my red food coloring group is in here, I'm going to say, listen, they're not rating it any differently than clear. As soon as they go outside of this 95%, in the extreme 5%, that means 2.5 and 2.5. Extreme 5, we got to split up. Okay? As soon as they go in the extreme 5%, then we're going to say, hey, these people don't look like people tasting clear solution, so the red food coloring must have made a difference. Everybody with me with the logic here? Okay? And we know the z-scores. We know the z-scores that define the middle 95%, that define the extreme 5%, right? Here's the cutoff. 1.96. 1.96. Okay? Plus, in this case, minus in that case. Okay? This is our definition for equal and our definition for unequal, right? If something's greater than z-score of 1.96, then we say it's too far out. It doesn't look normal. This is what normal looks like. This doesn't look normal. If the red food coloring folks are rating things just like the clear, then we would have a conclusion that the red doesn't make a difference. If the red food coloring group is out here or out here, then we're going to say that the food coloring made a difference. Okay? So this is what we're going to use as our criteria for our decision making. If I was flipping a coin 50-50, I'm not going to say it's unfair. 52-48, I'm not going to say it's unfair. 55-45, not 60-40, it's starting to make me nervous. At some point, we're going to say, no, coin's unfair. Same logic here, same logic. If our red food coloring group is in here, we're going to say, it's no different than clear. If it's here or here, higher or lower, then we're going to say there's a difference. So step 2 is referred to as setting the criteria. And what we're going to do is we're going to say, we're going to use an alpha, it's called an alpha level. Alpha is this symbol, like a fish, okay? We're going to say alpha of 0.05. Alpha of 0.05, okay? That's going to be our standard. It's almost for every question, it's just going to be alpha of 0.05. What does the 0.05 refer to? The extreme 5%. We're going to split that up into two tails. So 2.5% here, 2.5% here. That's what this z-score tells us. You can look it up in the table. Okay, look up a z-score of 1.96. The tail has 2.5%. 2.5, 2.5. Alpha of 0.05. That is the extreme 5%. Okay? It's called the alpha level. And typically, I'm going to have you say, okay, for alpha level of 0.05, we're going to use a z-score of plus and minus 1.96. Okay? I'm going to go back to this, and I'm going to say, when I say the red is not equal to the clear, that is, I'm going to say the red is making a difference. Okay? It's different than clear. What I'm talking about is the red food coloring group is in here or in here. Okay? if I end up saying the red food coloring, people are rating the sweetness the same as clear, that means they're in here somewhere. Okay? So step one, we're going to set up our hypotheses. Step two, we're going to identify to the reader, to the consumer, or to yourself. This is what I mean when I say not equal to, that it falls in the extremes. Okay? The next video, we'll get our little hypothetical sample of people tasting the red, and we're going to see what they look like. Now, I have a couple minutes, I think. I don't want to just ask one person to taste the red solution. If I do that, they may be unusual. They may be weird. They may have taste problems. They may really love red. They may have had experience with red food coloring that make them sick, or blah, 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 okay? What I want to do is, there is a hypothetical canvas bag full of 1 million people that would taste a 4% sucrose solution with red food coloring. I mean, it's hypothetical. It doesn't really exist. What I want to do is, I want to get the best guess for what's in that canvas bag. To get the best guess for what's in that canvas bag, should I ask one person to taste the red sucrose solution? Or should I have 4 people taste it? Or 14? Or 47? Okay? If I increase the size of my sample, instead of one person, I'm going to have 4 people taste the solution. The average for those 4 people should give me a better idea of what's in that canvas bag than just one individual. If I can get 14 people, that's going to give me a better idea of what's in that canvas bag than 4 people, right? What does that represent? As I increase my sample size, my standard error decreases. As I increase my sample size, I expect to be closer to whatever the average is of that bag, okay? So I want to use as many subjects as I can. And when you start doing research, either here at Utica College or when you go to graduate school, your mentor will say, we need more subjects, we need more subjects. They're not doing that just to make work for you. They know very well the more subjects that they have, the more confident they can be in their guess, right? If I'm trying to make a guess about the average, what's in that bag, I want the variability to be really small, okay? The way that I can do that is to increase sample size. Increase sample size, I decrease the standard error. What does that do to my confidence? If I increase the sample size, so I'm decreasing my standard error, I'm going to be more confident that I know what's in that bag. Okay? If I increase the sample size, it's going to decrease the standard error, give me a more confident guess about what's in the bag. I'd rather have a sample size of 20 than a sample size of 10. I'd rather have a sample size of 10 than a sample size of 4. Okay? Now, one more note, going a little bit late here. Sample size, I think they talk about this in the book. There are diminishing returns. After you get past about 30 subjects for your experiment, you're not getting a whole lot more benefit by adding more subjects. From 2 to 5, big benefit. 5 to 10, big benefit. 10 to 18, big benefit. But with every additional subject, you get less and less help. But it's always, more is always better, okay? As long as it's representative. So let's stop there, and we'll collect our data, and that's step 3. And then we'll figure out how to make our decision about whether or not the red food coloring made a difference. Oh, I just love this stuff, because we're actually answering research questions, and I'll use a whole bunch of other examples as well. All right, stay safe, everyone, and watch the video again if you need to. Email me questions if you would like. We're not going to do binomial distribution just to save some time, and you can do some practice problems in Chapter 7 to see if you're getting the feel for the central limit theorem, at least the computational part. Okay, I will see you the next time. Be healthy.